Hey everyone, and welcome to our first lesson in Unit 2. Today's lesson is going to be on kinematics, and before we get started on kinematics, we want to cover a little bit of background information on vectors and directions and what those mean exactly in regards to or through a physics lens. So a term that you're going to see, let me change my color pen here, a term that you're going to see often in this class is what we call a physical quantity. And a physical quantity is a property of a material that can be quantified by measurement. And all these quantities can be divided into two categories. And these you're going to see a lot of this year. Those categories are scalar and vector, two important physics terms. And a vector quantity is a quantity that is fully described. We describe a vector quantity fully and completely by its magnitude, which really is the size of the number, how big or small the number is, and its direction. We have a lot of vector quantities that, upon initial inspection, you might think, well, why do I need to describe the direction? And we'll get into those specific reasons for those specific quantities when we get to them. But any vector quantity has to be described in two ways, by the magnitude and the direction. For example, I might be traveling 10 miles per hour north. Whereas a scalar quantity can be fully described just by the magnitude of the number. So I could say that I'm traveling 10 miles per hour. For example, speed is a scalar quantity and could be described by just the magnitude, 10 miles per hour. If I can describe the motion given the direction, 10 miles per hour north, I can now talk about the object's velocity, which is a vector quantity. And as you'll see in your first lab this week, vector quantities are often represented by scaled arrows. And you'll get some practice in lab completing scale drawings to work on skills for drawing scale diagrams using vector arrows. And a vector arrow with an arrowhead is drawn in a proper length to scale, where I could represent a particular line as long as it is to scale, and this might represent 1,000 kilometers. And that vector arrow is going to have two components to it, a head and a tail. So we have the head and the tail. Now the magnitude and direction of that vector must be specified. When we draw it to scale, the actual direction that the arrow is pointing in and the size of that arrow are directly related to the magnitude and direction of the vector quantity. So when we start doing scale drawings in lab, all of your lines, depending on what you're drawing, have to have a specific representation of magnitude and direction. Now, kinematics is the branch of physics that deals with forces and the way that they produce motion or change in motion. And that overall branch is what we call mechanics. Kinematics is a branch of mechanics. So kinematics, and you might see some of these notes a little bit differently, because I've gone through and taken out some of the larger portions that were more writing. You guys currently don't have the updated version on that, so I'll get that to you as soon as possible. So kinematics is the mathematical treatment of the motion of bodies without regard, so we don't worry about the forces that produce the motion. We're just concerned about how the object's going to move after it's been sped up or slow down or change direction. And in order to do this, we need to understand the difference between distance and displacement. Here we'll get into the difference between scalar and vector quantities. So distance is the total length of a path that an object travels. Now, distance is a scalar quantity, meaning that we describe that quantity just by its magnitude. For example, if we consider this is my oval track. I can walk around the track from start to finish, and I can go some particular distance around there, and I can calculate that on the track. It is 400 meters. That's the distance. If I walk one lap, I'm going to go 400 meters. I don't have to give direction on that. My distance is described just by the magnitude of 400 meters. But displacement is the change in position. So it's the change in position of an object described by a vector that begins at the initial position of the object and ends at its final position. So if we consider my displacement, which is a vector quantity and has magnitude and direction, my displacement, if I start here and I go once around the track and I finish at that dot, what's my displacement? Feel free to pause the video at any time like this and try and answer the question that I'm posing. Well, if we start in the same spot that we finish, our displacement is 0. Whereas our distance, and yes, these are represented by the same variable, our distance would be 400 meters. I traveled 400 meters. That's the total length that I traveled. But my displacement, the change in position from where I started to where I ended, was 0. I ended in the same spot that I started in. So distance and displacement are usually measured in our SI unit of meters. We also might see it, depending on what we're talking about, in centimeters, or we'll go a couple bigger, 2 kilometers. Now our little buttoned up tuxedo guy up here, we'll show you a little bit difference here. If he's going to start at this 0 point, that's his starting point, he can travel. I'm going to move him to the left. And we'll take a look at a couple things. His position is minus 4.167. And he stopped right here. Now, in order to get to this spot, he traveled 4.167 meters. The negative, and we'll see this a lot this year, the negative is going to indicate a direction. So the negative direction in this case is to the left, and the positive direction is to the right. So he's traveling minus 4.167 meters, or 4.167 meters to the left. The negative is describing the displacement. That is the direction that this character has traveled. His displacement is 4.167 meters from his starting point, or minus 4.167. And the distance he traveled is 4.167 meters. No negative required because the distance that he travels doesn't need to be described by direction. Now if I move him back to that 0 point, well, he went down to 4 point, whatever that was, and then back, so his distance might be around 8 meters, but his displacement, since he ended up back where he started, is 0. And we can do something like this. We can make this guy travel all over the place. And we'll get into the velocity and acceleration later and how that produces changes in motion. But this guy's getting super tired, running for almost 4 seconds, 10 meters in either direction each time. And then we'll stop him, and we'll put him right back to where he started. And then I'm going to pause that. So the line here, if we follow the path here, this tells us the distance that the character travels. To the left, 8 meters. To the right, 10 meters. To the left, 9 meters. And back and forth he went. Well, he started at 0 meters, and he ended at 0 meters. So this character's displacement would be 0, and the distance he traveled would be the length of this line. We can add up the high and low values here and determine the total distance that he traveled, and that is different from the displacement. Now, displacement along the same straight line can be combined by simple addition or subtraction. So when we treat motion along the same line in the same dimension, let's say, we can just add those vector arrows by simple addition and subtraction. And I'll show you a couple examples of this. So we have a student that's going to walk 8 meters north and 17 meters north. We'll figure out what the resultant would be, or the result of the combination of different vector quantities. Now again, we're referring to displacement. So these are all going to be vector quantities. We can see that they're described by their direction as well. They're moving north. And I tend to always think of north as the top of a page. So we have our compass rose. For now, I would get used to drawing one of those in your responses just to indicate where and orient the reader, in this most cases myself, which direction you're referring to. And we know that this student starts somewhere and walks 8 meters. And that vector, since it's scaled, I'm going to try and keep this scaled. I'm not actually using the ruler here. But we'll consider that about 8 meters, and it's moving north. It's pointing in the north direction. And then he goes 17 meters. I'm going to try and draw this a little bit more than double. The one down here. And this is, and I'm going to keep it as 17.0 and 8.0 meters. Now, in order to figure out the total displacement, we're going to put these two vector arrows head to tail, end to end, and we simply combine them. Our level of precision will be in the tenths place, and what we get is 25.0 meters. Now that is missing one important piece of information, and this would have to be north, 25.0 meters north. So when we combine these, our combined vector looks something like that, 25.0 meters. Maybe he stops after 8 meters to get a quick snack break before he moves on for the remaining grueling 17.0 meters. Now in the next example, we have a student that's going to walk 3.0 meters east and then 15.0 meters west. What would the resultant be? So I'm going to draw our compass rose. And we have a student that's walking 3 meters east. So I'm going to go, we'll start here. We're going to go 3 meters east. And then walks 15 meters west. I'm going to assume that they turn around and they're just going to go. And that should be 5 times as big. Might not quite be that. And we're going to call this 15.0 meters. That's 3.0. What would the resultant be? Now, when we combine these, we always want to put vectors head to tail. Now, you can kind of just think about it. We're going to go 3 this way and then 15 that way. The difference is we can do some simple subtraction there. But we could also do this graphically, and we spend a whole unit on this later in the year. And I'm going to add those, and I'll show you what that means in a second. So we have one going east, we have the other going west. Now the difference between these two, if we were to put these head to tail and we wanted to shift this 3 meter one down here, the difference here is our displacement. And that difference, I'm going to do mathematically here, would be 12.0 meters. And this would be 12.0 meters west. So in this case, if I add these together, we could call the east direction negative and the west direction positive. In this case, this would come out to a plus 12.0 meters west, the positive direction indicating west. We could also do this as calling the west direction negative and the east direction positive. And we would get an answer of 12 meters, the negative indicating that it is going to the west. So again, just to show you that negative can be used to indicate direction. Now, so far, those have been pretty easy going in one plane, straight line. Well, a lot of motion doesn't necessarily move in that direction or in that way, right? So let's look at an example where we're not moving in. Well, I guess we'll wait on that one. We'll try one here where we're going in multiple directions with multiple turns before we get to the little crooked path there. So we have Kim who's going to walk 5 blocks north. I'm going to indicate that with a B, so now that looks kind of like a 6. So we'll just leave it as a 5. Kim's going to walk 5 blocks north, 8 blocks east, 5 blocks south to avoid a bad area. What is the displacement of Kim? Again, so the displacement is the change in position from where you start to where you end. And that difference is that right there. So we went north and over 8 blocks to avoid the bad area and then back down. So we really only changed our position along the x-axis. We're only displaced along the x-axis. Our y, we increased by 5 and then decreased by 5. So to find this displacement, we draw the arrow left to right, and we can see that this is 8 blocks as well. And that displacement, when drawn head to tail, would be 8 blocks east from where we started. Now, looking at vectors not in straight lines or at nice 0 or 90-degree angles, 180-degree angles, we can have vectors that move at different angles. We're going to keep this relatively simple for now. Now, if I wanted to travel from Buffalo to New York City to visit my son, what would my total displacement be? Well, let's consider going from Buffalo to New York City. And if we travel by means of the thruway, we're going to travel over to Albany and then down to New York City from our start to our finish. Now, our resultant vector, our displacement, is that vector right there, the change from where we started to where we ended. And it's always going to be a straight line. Now we know from A to B, and we'll call Buffalo A, And this will be point B. New York City can be point C. A to B is 289 miles, and B to C is 151 miles. What is our resultant? Well, digging up some of the old math skills that you have in your index and using page 5 on your reference tables, the geometry and trigonometry section of your reference table. If you remember, we can find one side of a triangle if we know the other two. This is a right triangle. Using the Pythagorean theorem, a squared plus b squared equals c squared. Now we have a right angle, and we know the two sides. So this is 289 miles squared plus 151 miles squared. And that's going to be equal to our resultant squared. Now this comes out to 106,322. We take the square root of that. That's equal to our r squared. Take the square root of that. And what we get is 326.07. That's equal to our resultant. And this, using significant figures, 3 and 3 in each of our 289 and 151, will round to 326 miles. Now that's our displacement or our resultant vector. The direction there would be southeast. If our drawing and our vector in our drawing is scaled, then the arrow, the direction that the arrow is pointing, is our direction of our displacement, and therefore we don't have to necessarily write it down in our answer. That's on a scale drawing. Now, in order to convert 326 miles into kilometers, which you want to make sure that we are able to do, we have 326 miles, and we have 1.61 kilometers for every mile. And when we cross multiply, we get an answer of 525 kilometers after our miles cancel. So that's how we will convert from a standard unit into a metric unit. If you guys have any questions, make sure you write them down and come get your questions answered. Hope you all have a great day.